Howdy, my name is Liam Hawley, and I'm going to be talking about the physics needed to make it into orbit. Before liftoff, there are many things that have to happen on the pad, including filling the rocket with the needed propellants and commodities for flight, as well as checking each of the working pieces of the rocket to make sure it's normal for launch. Before launch, the director has to give what's called the no-go or go-no-go poll, where every system must line up within a set margin, making sure that the vehicle is in a healthy working condition. At this point, each person has given the proper go-ahead for fueling of the rocket to start. And then as we make it towards the end of fueling, they make sure that every piece is correct on the computer, making sure that all the data lines up. And each part is in a healthy condition. At this point, the launch director gives that go, no-go poll for each system of the rocket. As we make it to the end, if everything is a go, then we are go for launch. And there we have liftoff of what is the Artemis 1 rocket with the SLS rocket. Starting our journey back to the moon as we explore more and create a on-the-moon base. And at the moment of liftoff, a few seconds before, the launch pad drowns in what is called the fire suppression system, as millions of gallons of water are shot underneath the rocket and all over the pad in order to minimize the damage from the sound vibrations and the massive explosion that is happening underneath the rocket. At the moment of the engine starting, the hold-down clamps are still engaged, which is what keeps the rocket on the pad. Even though there's a high thrust acting against the rocket, they still hold them down. As each engine comes to life, they throttle up to full throttle, and the computers check each of the engines and make sure that they're in healthy condition. And every system of the vehicle is working properly before finally pulling the release clamps and making it and starting the journey. As the hold down clamps disengage, the thrust becomes greater than the weight of the rocket, and the rocket starts to gain altitude while gaining velocity. Inside each of the rocket, we have the combustion chamber, and at this point, this is where the both of the propellants mix together and meet using what's called turbo pumps. These pumps have small holes, and they spin at a really fast rate and equally mix both of the propellants together. Inside of the combustion chamber, each engine has what is called an igniter, which is an electrode that ignites the propellants as they're mixed together. With the propellants, we either have our main fuel and the oxidizer. Sometimes rockets use hydrogen, or right now we are seeing an influx of methane-powered rockets, and also most older rockets use what's called hydrazine, which is another rocket fuel. And so both of these combine together and ignite. And because of that oxidizer, it's able to ignite. And so that causes a massive explosion to happen inside of the combustion chamber. And because of the way that the rocket engine is designed, with the bell at the end, it pushes that explosion at a controlled rate, which creates a force that acts against the rocket. And so we want, just like miles per gallon, you want to have a high efficiency fuel. And so the least amount of fuel that you can burn to reach a greater velocity is always the goal. And so with Newton's third law, for every action there is an equal or opposite reaction. We take into account the force of those explosions happening from the rocket. And as the thrust of each engine gains, is higher than the weight of the rocket, it starts to push up and the rocket gains kinetic energy as well as gaining altitude. Even though we're gaining altitude and kind of gaining GPE, or the gravitational potential energy, the velocity is made because it starts at sea level. The kinetic energy comes from the explosions from the rocket. So with that, the velocity increases as the engines push against the rocket. And so the rocket starts to go into a roll maneuver as it turns itself to become more aerodynamic. And so this is needed so that it can get through the thickest parts of the atmosphere. And this is very important so that the rocket body does not disintegrate or disassemble in air. And so after doing the roll maneuver, it does what's called a gravity turn as it follows an exponential arc into orbit. So instead of a rocket going straight up, it follows an arc so that it can so that it goes parallel to the surface of the Earth and gives it a more seamless ride to space. If the rocket were to go straight up, the force of gravity is too strong and it wouldn't make it fully into orbit. And so to make it into orbit, you do a circulation around the Earth. And so you're trying to go at a parallel to the surface, and that's what causes our orbit. And because of the speed of the rocket, it is able to miss the surface and just keeps falling in a controlled way. During this time of altitude gain, the atmospheric pressure is decreasing as you go up into the upper levels of the atmosphere. And with more force pushing against the bottom of the rocket with the engines, the rocket has very high pressure up on the bottom and low pressure pushing on the top. So like a soda can, if it's unpressurized, you can crush it. But when it is pressurized and you haven't opened it, it is very rigid. And that's what we want. So as the propellant is used to gain velocity, the tanks have to remain at a constant pressure so that at this point of what we call max Q, or maximum aerodynamic pressure, the rocket is not going to collapse like a soda can would. So this is a lot for the engineers and the masterminds behind the rocket, and it takes a lot to understand how this works and get it in a proper working condition. So here we have the Falcon 9 following this gravity turn. As you can see, it follows an arc path and ends parallel to the surface of the Earth. This is a Falcon 9 long exposure image, so it highlights the light trail that happens from it. Also here we have Space Shuttle Discovery showing the roll and the gravity turn, as you can see with its contrail from the SRBs, or the solid rocket boosters on the side. It creates this smoke trail, and it gives us a good idea of how it starts to turn. Over here we have the same Shuttle Discovery doing what is called the roll maneuver, where it points the actual space shuttle underneath the rocket, and it makes it more aerodynamic as it reaches orbit and travels through the atmosphere. And so liftoff is the hardest thing that we really get to, because once we're in the air, you have made it through the most difficult part. As the engines are working properly, it's just a matter of making sure that they're healthy. And so by the time we get to the upper levels of the atmosphere, the rocket is traveling at close to 6,000 kilometers an hour, traveling at a distance parallel to the surface of the Earth. And this large gain is needed to get a push into the orbital trajectory. And also with rockets nowadays, having a single stage to orbit is not that common. So rockets usually have 2 or more than 2 stages, and at this point they separate or stage, where the first stage is left behind and the second stage continues. On the second stage, there is usually a vacuum optimized engine, which has a different bell and nozzle shape that expands the exhaust plume at a more efficient rate while being in the vacuum of space. The second stage is what holds on to the payload, and as it continues to travel onto its intended orbit, or stable orbit, the first stage then comes back and either burns up in the atmosphere or like with SpaceX, they're able to take them and land them and reuse them after each other. So when the second stage separates, it moves on and travels into space, and as it leaves the atmosphere, it lets go of the fairing covers, which protect the payload during that atmospheric part, so the friction that's happening on the nose cone is not put onto the payload itself. And so in the vacuum of space, we don't have much friction, so they can let go of these fairing halves, and they just travel back down to Earth. Sometimes they travel in a good manner and don't burn up. Sometimes they burn up and is no longer used. Because of the speed that the second stage is traveling at in space, there's minimal friction, so we don't need a constant acceleration to maintain that speed. So once you get up to your top speed, you're going to stay at that unless something else is acting on you, whether you hit something or something hits you and your path is kind of obstructed. At this point, the rocket is almost falling to the surface of the Earth, and because of its speed, it narrowly misses the surface and continues to fall. And so because of gravity pulling it down, it starts its orbit. And so once we make it to our parking orbit or stable orbit where the payload is supposed to be, we can release the payload. And then after that, the payload satellites usually have their own engines that they use to make it into their own operating orbit. And so here we have SpaceX's Starlink satellites. These are the version 2, separating from the second stage of the Falcon 9. And some wonderful views of the Earth right there. And you can see they travel off, and even though they're veering off into a different direction, they have their own thrusters that move them into their perfect orbit. And mission success. After letting go of the payload, the rocket has done its job, and now it's on to the owners of the payload and the operators to get it to where it needs to be and to get it into like working condition by opening up all of its solar panels and antennas and making sure that they can connect with it and communicate with the satellite at a proper, in a healthy way. And so because of the high density of the atmosphere, most vehicles traveling back into it don't make it and they burn up. But like here with Starship, it incorporates this large heat shield, which is built of many tiles. Like the space shuttle, it is on the belly of the rocket, and as the rocket travels down into the atmosphere, these heat shield tiles have a high, they dissipate heat at a high level. So with these, you can see some people put them in furnaces, and within a minute, you're able to grab it, even though it's glowing red hot. It doesn't burn because of its mainly ceramic alloy makeup. And so most vehicles that are trying to make it back into this to the surface use these heat shields so that they can withstand the high friction and the heat that is built when it enters the atmosphere. If it doesn't have this, it will rapidly disassemble and burn up, which is a cool sight if you ever get to see. Just a beautiful thing to watch it disassemble in the atmosphere. It's like a very nice light show. So sometimes it doesn't always go to plan, but also explosions happen because you are working with very explosive fuels and oxidizers. It is just perfect conditions for explosions to happen. Here we have what is called a RUD, or a rapid unscheduled disassembly, during a pre-flight test of the SpaceX Falcon 9 rocket, doing engine fires, or a static fire. One of the helium tanks in the upper second stage leaked and caused an explosion in the second stage, which then traveled down to the first, ending in a massive explosion, destroying a lot of the working parts of the pad, leading to almost 6 months of work that had to be done. And with this, they had the payload on board during the test, and so sadly, at the end of this explosion, you can see the payload fall to the ground and further explode, which, hard to say, it's cool to watch, but all those people who were in the control room are most definitely very depressed. Sometimes we have it where explosions are scheduled, like this where SpaceX was testing the Crew Dragon escape system, where if something were to happen with the rocket itself and with crew on board, they're able to eject all of the people and land them back down safely. And so here we have it going up through the hardest parts where max Q, like I said, the most aerodynamic pressure. And the rocket cuts off with an engine malfunction caused by the SpaceX team itself. In this, you can't see the capsule move on, but there we see the Falcon 9 explode as they triggered the flight termination system, leading to a scheduled disassembly. This was needed to test the major important factors of the rocket so that they could get a certification for the crew to be able to launch them back to the ISS from America for the first time in almost 11 years.